Section. Introduction. In our work, we primarily focus on guiding or aligning current models using reinforcement learning from human feedback, RLHF. This involves encouraging behaviors that human evaluators rate positively and discouraging those they rate negatively. This method works well when human evaluators can easily determine whether a model's behavior is good or bad, and it's a key part of training modern language model assistants like ChatGPT. However, we anticipate that future models will be capable of complex and creative behaviors that may be beyond human comprehension. For instance, if a highly advanced assistant model generates a million lines of extremely intricate code, humans may struggle to provide reliable supervision for crucial alignment-related tasks. These tasks could include determining whether the code aligns with the user's intentions, whether the assistant model is providing honest answers about the code, and whether the code is safe or dangerous to execute, among others. If we fine-tune a highly advanced model with human supervision on a reward modeling, or safety classification task, it's uncertain how that model will generalize to complex behaviors that humans couldn't reliably supervise themselves. This presents a fundamental technical challenge. How can less advanced supervisors control models that are much smarter than them? Despite the significance of this issue, it's challenging to study empirically today. Previous work on alignment has either directly tackled this core challenge, primarily through theoretical frameworks and simple problems, or has studied humans supervising current models, without addressing the core challenges that may arise with more advanced models. Ideally, we'd like a setup that captures the core challenges of aligning future advanced models while also allowing us to make iterative empirical progress today. We propose a simple setup for studying the problem of humans supervising advanced models by considering an analogy. Can we use less advanced models to supervise more advanced models? We can test this empirically by fine-tuning large, advanced, pre-trained models on labels generated by small, less advanced models and observing how they generalize. We call this the weak-to-strong learning problem. Why might weak-to-strong learning be possible? On one hand, the advanced model could simply learn to imitate the less advanced supervisor, including its errors, since that's what we would naively train it to do. On the other hand, advanced pre-trained models should already have good representations of the alignment-relevant tasks we care about. For instance, if a model can generate complicated code, then it should also know whether that code faithfully adheres to the user's instructions. Therefore, for alignment purposes, we don't need the less advanced supervisor to teach the advanced model new capabilities. We just need the less advanced supervisor to bring out what the advanced model already knows. This gives us hope that the advanced model can generalize beyond the less advanced supervision, solving even difficult problems for which the less advanced supervisor can only provide incomplete or flawed training labels. We call this phenomenon weak-to-strong generalization. We study our weak-to-strong learning setup by fine-tuning base, i.e., pre-trained only, language models from the GPT-4 family, spanning 7 orders of magnitude of pre-training compute, across 3 settings: a large set of popular natural language processing, NLP, benchmarks, chess puzzles, and our internal ChatGPT reward modeling dataset. Our main findings include: 1. Advanced pre-trained models naturally generalize beyond their less advanced supervisors. If we naively fine-tune advanced models with labels generated by less advanced models, they consistently outperform their less advanced supervisors. For example, on NLP tasks, if we fine-tune GPT-4 with labels from a GPT-2 level model, we typically recover about half of the performance gap between the two models. 2. Naively fine-tuning on less advanced supervision is not enough. Despite positive weak-to-strong generalization, there's still a substantial gap between advanced models fine-tuned with less advanced supervision and advanced models fine-tuned with ground truth supervision. 3. Weak-to-strong generalization is particularly poor for ChatGPT reward modeling. Collectively, our results provide empirical evidence that naive RLHF will likely scale poorly to superhuman models without additional work. 4. Improving weak-to-strong generalization is feasible. We find that we can improve performance by encouraging advanced models to have confident predictions with an auxiliary loss, bootstrapping supervision with intermediate models, and improving model representations with unsupervised fine-tuning. However, our work has important limitations. None of our methods work consistently in all settings, and especially in the setting, we are still far from recovering the full performance gap between less advanced and advanced models. Thus, our methods serve more as proofs of concept that weak-to-strong generalization is feasible, rather than practical solutions we recommend deploying today. Furthermore, there are still important differences between our empirical setup and aligning superhuman models that we did not address. Continuously refining our basic setup will be important for ensuring that research today continues to make real progress toward aligning the superhuman models we develop in the future. Despite the limitations of our work, we find our results to be highly encouraging. We show that substantial weak to strong generalization is not only possible, but actually a widespread phenomenon. We also show that with very simple methods, we can drastically improve the ability of less advanced supervisors to elicit knowledge from advanced models. With much more progress in this direction, we could get to the point where we can use less advanced supervisors to reliably elicit knowledge from much stronger models, at least for some key tasks that we care about. This may allow us to develop superhuman reward models or safety classifiers, which we could in turn use to align superhuman models. Aligning superhuman models is essential for making them safe. There is increasing recognition that failing to align such powerful models has the potential to be catastrophic, making this one of the most important unsolved technical problems in the world. We believe it is now more feasible than ever to make rapid iterative empirical progress toward solving this problem. Section Summary. The section discusses the challenge of aligning superhuman models with human supervision. While reinforcement learning from human feedback, RLHF, is effective for training models like ChatGPT, it becomes difficult when models generate complex behaviors that humans cannot fully understand or supervise. To address this, the authors propose a setup where weak models supervise strong models, testing the phenomenon of weak to strong generalization. They find that strong models can generalize beyond weak supervision, but there is still a performance gap compared to ground truth supervision. However, they show that simple methods can improve weak to strong generalization, offering hope for aligning superhuman models and making progress towards solving this important technical problem. Section. Related work. In this section, we delve into the various research areas that are closely related to our study. Our primary focus is on how we can use the generalization capabilities of deep neural networks to transition from weak to strong learning. Firstly, we look at weakly supervised learning. This is a type of learning where models are trained using labels that may not be entirely reliable. There's a wealth of research on this topic, especially on learning from noisy labels. Techniques such as bootstrapping, noise-robust losses, and noise modeling are commonly used. However, our weak supervision presents a unique challenge as the errors are not uniform but are dependent on individual instances. Semi-supervised learning is another related area. Here, labels are only available for a portion of the data. We could apply this to our study by having a subset of easy examples with reliable labels from weak supervisors and a subset of hard examples without labels, which we refer to as easy to hard generalization. Next, we consider the student-teacher training framework. This involves training a teacher first and then training a student based on the teacher's pseudo-labels. This method is widely used in semi-supervised learning, domain adaptation, and knowledge distillation. Unlike previous studies, we focus on scenarios where the student is more capable than the teacher. We also explore cases where the student is at least as capable as the teacher. We also look at the robustness of pre-training and fine-tuning. Many studies have shown that pre-training on diverse data leads to more robust representations that generalize better. Fine-tuning usually improves generalization within the distribution but often performs poorly outside of it. Some recent solutions to this problem include weight ensembling, fine-tuning only a subset of layers, or mitigating the distortion effects that fine-tuning has on pre-trained features. In our weak to strong generalization, the weak labels contain a specific form of bias due to the weak model's lack of capability. There's a lot of research on learning from biased training data. However, most of this work focuses on known biases. Our setting presents a unique challenge as the bias is unknown. Imitation and preference learning are also relevant to our study. The goal here is to guide already capable models to do what we want them to do. However, both these methods assume high-quality human supervision, which may not be applicable for superhuman models. Scalable oversight techniques aim to enhance the ability of humans to supervise models. For instance, humans may ask models to critique the outputs of other models, or use models to help break down a problem into simpler sub-problems. Unlike these methods, we aim to generalize beyond human supervision so that models perform well even in settings we cannot reliably supervise. Finally, we consider knowledge elicitation and honesty. This involves eliciting latent knowledge from a superhuman machine learning model even under worst-case assumptions. For instance, a special case of this is honesty, where the goal is for the models to report their true beliefs. Our setting can be viewed as a general methodology for empirically studying problems like this across a wide range of tasks. Section Summary. The paper explores the concept of weak to strong learning and its connection to various research areas such as weakly supervised learning, learning from noisy labels, semi-supervised learning, student-teacher training, robustness of pretraining and fine-tuning, debiasing, imitation and preference learning, scalable oversight, and knowledge elicitation. The authors highlight the differences and similarities between their approach and previous work in these areas, emphasizing the need for methods that can handle qualitatively weak supervision and enable models to generalize beyond human supervision. Section: Methodology. In this study, we're tackling a unique problem. How can a less intelligent supervisor manage a model that's much smarter? This is what we refer to as the weak to strong learning problem. To simplify this, we're using a basic analogy where we replace the human supervisor with a less intelligent model supervisor. Here's how we're going about it. 1. We start by creating a weak supervisor. We do this by fine-tuning smaller pre-trained models using actual labels. We refer to the performance of this weak supervisor as the weak performance. We then generate weak labels by using the predictions of the weak model on a separate set of examples. 2. Next, we train a more intelligent student model using the weak supervision. We fine-tune this stronger model using the weak labels we generated earlier. We call this the strong student model, and its performance is referred to as the weak to strong performance. 3. Lastly, we train a strong model using actual labels for comparison. We call the performance of this model the strong ceiling performance. This should ideally represent the full capabilities of the strong model. We then measure the performance gap recovered, PGR, which is the fraction of the performance gap, the difference in performance between the weak and strong ceiling models, that we can recover with weak supervision. If the weak to strong model performs as well as the weak supervisor, then PGR is 0. If it generalizes perfectly, PGR is 1. Our approach has several benefits. It can be studied with any pair of weak and strong models, making it easy to study scaling laws without needing expensive state-of-the-art models. It doesn't require human involvement, so feedback loops are quick. It can be studied for any task of interest, making it easy to empirically test across a wide range of settings. However, our approach also has limitations. For instance, our strong models may not have learned features relevant for imitating weak model predictions. Also, our pre-training data implicitly contains supervision from humans, making it artificially easy to elicit strong models' capabilities. In this study, we used 22 popular natural language processing benchmarks, chess puzzles, and ChatGPT reward modeling. We converted all datasets to binary classification tasks and balanced the classes. We produced soft labels from the weak model. For the chess puzzles, we predicted the first move played, which is the best move in the given chess position. For the ChatGPT reward modeling, we trained a reward model to predict human preferences between model responses. We believe that refining our methodology to produce even more analogous setups is a key priority for future work. Section Summary. In this section, the authors discuss the methodology of their study, which focuses on the weak to strong learning problem. They create a weak supervisor by fine-tuning small pre-trained models on ground truth labels and generate weak labels by taking the weak model's predictions on a held-out set of examples. They then train a strong student model with the generated weak labels and compare its performance to a strong model trained with ground truth labels. The authors define the performance gap recovered, PGR, as the fraction of the performance gap between the weak and strong ceiling models that can be recovered with weak supervision. They highlight the advantages of their setup, such as its flexibility and efficiency, but also acknowledge its limitations, including the potential mismatch between weak and superhuman models and the artificial ease of eliciting strong models' capabilities due to pre-training data. The authors conclude the section by mentioning the main empirical results of their study, which include tasks from popular natural language processing benchmarks, chess puzzles, and ChatGPT reward modeling. Section: Naively fine-tuning on weak labels. We've been exploring how well advanced learning models can adapt when they're fine-tuned using labels created by less sophisticated models. We've looked at this in 3 different contexts: natural language processing tasks, chess puzzles, and reward modeling. We've been using models from the GPT-4 family, which allows us to examine a wide range of differences in computational power between the advanced models, the students, and the less sophisticated models, the supervisors. Our findings show that the advanced models almost always perform better than their less sophisticated counterparts. This is true across almost all the different scenarios we've studied and regardless of the size of the models. In natural language processing tasks, we've found that advanced models trained with less sophisticated supervision can often perform significantly better than the less sophisticated model itself. Even when the less sophisticated model is very basic and the advanced model has a lot more computational power, we can still close more than 20% of the performance gap. The performance gap reduction, PGR, increases both with the size of the less sophisticated model and the size of the advanced model. For the largest models, the PGR is often above 50%. However, the results are more mixed when it comes to chess puzzles. When we use the smallest, less sophisticated models, the PGR is close to 0 and the test accuracy curves appear flat. But as the size of the less sophisticated model increases, the PGR also increases significantly. In contrast to the natural language processing tasks, where PGR improves with the size of the advanced model, PGR decreases with the size of the advanced model for a given less sophisticated model in chess puzzles. In the ChatGPT reward model setting, we find that the generalization from less sophisticated to advanced models is poor by default. We're usually only able to close about 10% of the performance gap between the less sophisticated model and the advanced model. Despite these findings, we're optimistic that improving the generalization from less sophisticated to advanced models is a feasible task. We've found that we can use simple methods to significantly improve this generalization. One such method is bootstrapping with intermediate model sizes. The idea is to first align a slightly more advanced model, use that to align an even more advanced model, and so on. We've tested this idea in the chess puzzle setting. When we fine-tune the advanced models using labels from the less sophisticated models, we see high PGR when the gap between the models is small, but low PGR for larger gaps. So, in this setting, it might be helpful to take multiple small steps, where PGR should be high, instead of one big step. For each round of bootstrapping, we run 3 iterations of learning from less sophisticated to advanced models. We've found that bootstrapping improves PGR compared to the baseline, especially for larger advanced models. With the naive method, transfer accuracy curves flatten as the gap between the less sophisticated and advanced models grows larger. But with bootstrapping, the accuracy continues to improve. However, in preliminary experiments, we've only seen small improvements with bootstrapping on natural language processing tasks and no improvements in the reward modeling setting. Overall, these results suggest that bootstrapping is a promising approach for improving the generalization from less sophisticated to advanced models in some settings. But naive bootstrapping alone won't be enough to align models that are much more advanced than their supervisors. Section Summary. In this section, the authors evaluate the performance of strong models when fine-tuned on weak labels generated by weak supervisors in 3 different settings: NLP tasks, chess puzzles, and reward modeling. They find that in most cases, the strong models outperform their weak supervisors, with particularly promising results in NLP tasks where strong models trained with weak supervision can achieve substantially higher performance than the weak models themselves. However, the results are more mixed in the chess puzzle setting, and weak to strong generalization is poor by default in the reward model setting. The authors also propose a method called bootstrapping, where they align models of increasing sizes in a sequence and use weak labels from each model to fine-tune the next one. This approach shows improvements in the chess puzzle setting, but only small improvements in NLP tasks and no improvements in the reward modeling setting. Overall, the results suggest that while weak to strong generalization is possible, naive fine-tuning alone is insufficient, and new techniques are needed to align strong models with weak supervision. Section. An auxiliary confidence loss can dramatically improve generalization on NLP tasks. We've discovered that incorporating an auxiliary confidence loss can significantly enhance the generalization of natural language processing, NLP, tasks. In our initial experiments, we simply fine-tuned the more advanced model, which we'll call the strong student, based on the labels provided by the less advanced model, the weak supervisor. However, this approach has a downside. the strong student might also learn to mimic the weak supervisor's mistakes. To avoid this, we want the strong student to understand the weak supervisor's intentions without copying its errors. We achieve this by adding an auxiliary confidence loss term to the standard cross-entropy objective. This technique is similar to conditional entropy minimization, a well-known method in semi-supervised learning. In essence, we added an extra loss term that bolsters the strong model's confidence in its own predictions, even when they contradict the weak labels. We've provided a detailed explanation of this method in a separate section. When we applied this method to our NLP tasks, we found that it slightly underperformed the simple baseline for smaller strong students. However, it significantly improved generalization when there was a large computational gap between the weak and strong models. With the smallest weak supervisor and largest strong student, the confidence loss boosted the median performance gain ratio, PGR, from about 25% to nearly 80%. We also plotted generalization curves for a representative subset of NLP datasets. In some cases, the confidence loss didn't help much or even degraded performance. This was particularly true when the gap between the weak supervisor and strong student was small, or when the dataset featured inverse scaling even with ground truth supervision. However, the confidence loss dramatically improved performance on most NLP datasets. In many cases, we achieved almost perfect generalization, recovering nearly all the performance of the strong model, even when using the smallest weak supervisors. We also found evidence supporting our initial intuition for the confidence loss. It allowed the strong student to confidently disagree with its weak supervisor. The auxiliary loss reduced the strong student's imitation of weak errors and mitigated overfitting to weak labels. Understanding the generalization from weak to strong models is crucial for developing reliable methods. We studied two phenomena relevant to this: the imitation of supervisor mistakes and the relevance of the tasks to the strong student model. When we train a strong model with weak supervision on a task, we hope that the strong model will perform that task as well as possible, using its pre-existing capabilities to significantly outperform the weak supervisor. However, if the weak labels contain systematic errors that are easy to learn, the strong model could learn to imitate those errors. Overfitting to weak supervision is a particular concern. In theory, fitting the weak labels perfectly should result in perfect imitation and a PGR of 0. However, in practice, we train on finite data for a small number of epochs. We found that the strong student often overfits to the weak supervisor's errors. We also found that early stopping or regularization strategies could substantially improve weak to strong generalization by reducing overfitting to the weak labels and their errors. For instance, the auxiliary confidence loss we introduced earlier significantly reduced overfitting to weak labels on NLP tasks. For large weak-strong gaps, early stopping on ground truth, compared to early stopping on weak labels, gave a 15% PGR boost when using the naive method, but only a roughly 5% PGR boost when using the confidence loss. Section Summary. An auxiliary confidence loss is proposed to improve generalization on NLP tasks by preventing the strong student model from imitating the errors of the weak supervisor. This method reinforces the strong model's confidence in its own predictions, even when they disagree with the weak labels, resulting in significant improvements in generalization for large gaps in compute between weak and strong models. Additionally, overfitting to weak supervision is observed, and the auxiliary confidence loss helps mitigate this issue by reducing overfitting to weak labels and their errors. Section: Student-Supervisor Agreement. We're going to discuss the concept of student-supervisor agreement, which is a way to gauge how well a student model is imitating its supervisor model. This is done by looking at the percentage of test inputs where the student model's prediction matches that of the supervisor model. If the agreement rate is 100%, then the accuracy of the student model, when transitioning from a weak to a strong model, would be the same as the supervisor model's accuracy, and the performance generalization ratio, PGR, would be 0. In our observations, we found that for our basic fine-tuning model, the student-supervisor agreement is consistently high, often higher than the accuracy of the weak supervisor model. This suggests that the student model is also replicating some of the supervisor model's mistakes. This pattern is seen across all tasks, including natural language processing tasks, chess, and reward modeling, and for all model sizes. We also found that the confidence loss, which encourages the student model to make confident predictions even when they contradict the supervisor model, significantly reduces student-supervisor agreements. This is primarily because it reduces the imitation of supervisor models' mistakes. In some cases, the confidence loss reduces the student-supervisor agreement below the strong student model's test accuracy, meaning the model is fitting the ground truth concept better than it is fitting the weak labels it was trained with. Next, we looked at student-supervisor agreement in relation to the size of the strong model. Interestingly, we found that larger student models consistently agree less with the supervisor model's errors than smaller student models, despite being trained to imitate the supervisor model. This trend is particularly strong when we evaluate agreement only on data points where the supervisor model is wrong. These results suggest that pre-trained models may struggle to fit the errors of other smaller pre-trained models, especially in fine-tuning settings with limited data. We also conducted initial experiments to test how different types of weak supervision errors impact what the strong student model learns. Our results suggest that errors that are harder for the student model to imitate result in stronger weak to strong generalization. However, even when the errors are easy to imitate, the confidence loss can help. We then explored the concept of saliency in the strong model representations. We hypothesized that weak to strong generalization might be feasible when the task or concept we want to elicit is internally salient to the strong model. We also considered the possibility that eliciting what the strong model knows is easy, particularly if strong pre-trained models can solve many relevant tasks zero-shot with a simple prompt. We found that zero-shot and five-shot test accuracy is poor for most model sizes but improves drastically for larger model sizes. For the largest models, five-shot prompting becomes competitive with fine-tuning on many tasks, indicating that eliciting the task-relevant knowledge of these very large models is relatively straightforward. However, we found that weak to strong learning is a non-trivial problem in the prompting setting as well. Similar to the fine-tuning setting, few-shot weak to strong performance improves for stronger supervisors. But weak to strong fine-tuning with the confidence loss generally outperforms weak to strong few-shot prompting. Overall, these results suggest that for the largest model sizes, the knowledge needed to solve many tasks can be elicited fairly easily with prompting. However, our current setup may be more disanalogous for prompting than for fine-tuning. Many of our natural language processing tasks may have been implicitly observed during pre-training, which we conjecture benefits prompting more than fine-tuning. Section Summary. The student-supervisor agreement is a measure of how closely the student's predictions align with the weak supervisor's predictions. In our experiments, we found that the student often imitates the supervisor's errors, resulting in high agreement. However, when using the confidence loss, the student imitates the supervisor's mistakes less, leading to lower agreement and better fitting of the ground truth concept. Additionally, we observed that larger student models tend to agree less with the supervisor's errors compared to smaller models, suggesting that pre-trained models struggle to fit the errors of other pre-trained models. Section. Generative supervision improves weak to strong generalization. We've discovered that enhancing the prominence of a task in a model can improve its ability to generalize from weak to strong. This can be achieved without the need for ground truth labels by using unsupervised fine-tuning with a language modeling objective on data relevant to the task. For instance, if we fine-tune a language model on online reviews, the model will develop a strong internal representation of sentiment. We tested this approach in our reward modeling setting, where we typically initialize the model with a baseline fine-tuned on demonstrations of desired behaviors. Instead of introducing a new supervision dataset, we use the ChatGPT comparison data. This data consists of a prefix, a single request or conversation between the user and assistant, and at least two possible completions. We fine-tuned the base models on all prefix completion pairs, disregarding the human preferences between the completions. It's important to note that this process includes completions ranked worst by human raters, so it shouldn't leak any information about the ground truth preference labels that the weak to strong models shouldn't have access to. However, since the completions can come from humans or stronger models, there may be some leakage similar to the pre-training leakage that we discuss elsewhere. Despite these challenges, the reward modeling task is still complex, and we plan to address this issue in future work. We found that additional generative fine-tuning on the reward modeling data improves weak to strong performance. This procedure also enhances the performance of models trained on ground truth reward modeling data. We compared our new weak to strong performance to strong, ceiling models that were also first generatively fine-tuned in the same way. We found that generative supervision improves performance by approximately 10 to 20%. When we combine this with ground truth early stopping, we can achieve a performance improvement of approximately 30 to 40%. This makes the results on the reward modeling task competitive with the weak to strong generalization we observe on natural language processing and chess puzzle tasks. We believe that this approach of improving task prominence with generative fine-tuning on relevant data could be applied to all settings and could be a promising direction for future work. One way to measure task prominence is by how linearly a task is represented. We can measure the performance of a linear probe, logistic regression classifier, trained from frozen activations of the model. If the optimal solution can be approximately recovered with a linear probe, that could simplify our problem greatly. In our work, we focused on how linearly a task is represented in the final activations, prior to the unembedding layer. We found that we can achieve better performance by first fine-tuning the model on the weak labels, and then linear probing using the ground truth labels. This means that when we fine-tune the strong model with weak labels, the representations become more linear even with respect to ground truth labels. This approach outperforms the naive weak to strong fine-tuning baseline and is closely related to a recent finding in the spurious cues literature. They found that fine-tuning a model on biased supervision can result in models with very biased outputs, but surprisingly strong linear representations of the desired concepts. These results suggest an alternative approach to improving weak to strong generalization. We could first linearize the desired concept by naively fine-tuning on weak labels. Then we could use simpler linear probe-based weak to strong methods to elicit the desired concept. Section summary. Generative supervision can enhance weak to strong generalization by increasing the salience of the desired task to the strong model. This can be achieved through unsupervised fine-tuning with a language modeling objective on relevant data. The combination of generative fine-tuning and ground truth early stopping can significantly improve weak to strong performance, making it competitive with other tasks in NLP and chess puzzles. Additionally, fine-tuning on weak labels followed by linear probing with ground truth labels can lead to more linear representations of the desired concepts, improving overall performance. Section. Discussion. In this study, we introduced a straightforward comparison to help us understand the key challenge of aligning superhuman models. We demonstrated that it's possible to make significant strides in this area. However, our approach still has some limitations, which we'll discuss further. We'll also suggest some potential directions for future research. One limitation is the issue of imitation saliency. Superhuman models might easily mimic minor errors. Future models are likely to be very good at predicting human thoughts and speech, especially if they're trained on human data like current models. If we train a superhuman model with human supervision without careful consideration, it might just mimic the human supervisor, showing human-level abilities instead of its potential superhuman abilities. Our current setup only partially addresses this issue. While our advanced pre-trained models do mimic weaker supervisors to some extent, they're not specifically pre-trained to mimic weaker models. Our findings suggest that larger, more advanced models might even struggle with this imitation. Therefore, the issue of imitating the weak supervisor might not be as significant in our setup as it will be in the ultimate problem. This could lead to inflated generalization performance today. We believe that a more detailed examination of this issue is a crucial area for future research. Another limitation is pre-training leakage. Superhuman knowledge might be hidden and not observable. Many of the tasks we consider in this study might have been indirectly observed during pre-training, for example, through online forum questions or slight task reframing. However, future superhuman models might never directly observe superhuman alignment-relevant abilities. These abilities might be primarily hidden, learned through self-supervised learning or reinforcement learning rather than imitation learning. Intuitively, hidden abilities might be harder to bring out than abilities that models could have seen in their pre-training data. This discrepancy could make our results overly optimistic. We hypothesize that this discrepancy also boosts prompting performance more than it boosts fine-tuning performance. If this is true, prompting would be more of a discrepancy in our setup than fine-tuning. We plan to test this hypothesis in future research. In terms of future work, what would convince us that we have a solution? This is a complex question, and we don't claim to have a complete answer. However, we anticipate that significant progress in at least 3 areas will be necessary. analogous setups, scalable methods, and a solid scientific understanding. We'll now outline specific problems for each of these areas. For analogous setups, having robust measurements and a reliable methodology is crucial for making empirical progress in any field. It's important that we have metrics that give us a strong indication of whether we're making real progress toward the problem we ultimately care about. Important directions for future work include making our setup more analogous by addressing the main remaining discrepancies described earlier. Analogous setups are crucial to ensure that methods that work today will continue to work for superhuman models. We should also validate that discrepancies are not severe, for example, by checking that results are qualitatively similar when using, for example, third-grade humans to supervise our strongest models today. We should also relax some of the simplifications we made, for example, by generalizing our methods and results to more complex generative tasks. We should test how robust our weak to strong classifiers are to optimization pressure when we achieve high PGR. We should also test our hypothesis that prompting-based methods in our current setup will not be as indicative of future results compared to fine-tuning-based methods, and improve our setup to fix this. We should identify new or more specific discrepancies with our setup and address them. Furthermore, we don't yet know what future models will look like. We should update our setup over time as we learn more about how broadly superhuman models will be built. Section Summary. The authors propose a simple analogy for studying the challenge of aligning superhuman models and demonstrate significant progress in this area. However, they acknowledge important differences between their setup and the ultimate problem, such as the potential for superhuman models to imitate weak errors and the presence of latent knowledge that may not be directly observable. They suggest that future work should investigate these disanalogies and focus on creating analogous setups, developing scalable methods, and gaining a strong scientific understanding to make further progress in this field. Section. Concrete problems, scalable methods. We believe that significant advancements in weak to strong generalization are achievable. This is because the strong model should already have a comprehensive understanding of the task at hand. It should have meaningful representations of the task, and all we need to do is extract this knowledge. This leads us to several characteristics that the desired generalization should possess, and we might be able to measure these without needing access to the ground truth. Firstly, the desired generalization should be able to disagree with the weak supervision when it's incorrect. This is something our auxiliary confidence loss might be able to capture. Secondly, the desired generalization should be natural, or salient, to the model. In other words, we shouldn't have to modify the model significantly to bring out the desired concept. Lastly, the desired generalization should be consistent. This consistency can range from basic logical consistency to complex forms of consistency between many prompts, such as cycle consistency and cross-examination. In the future, we should identify more unsupervised properties that can help define the desired generalization. There are likely existing methods in the machine learning literature, like semi-supervised learning or robust fine-tuning, that could be beneficial and lead to substantial improvements in weak to strong generalization. Approaches based on generalization to weak to strong learning can work hand in hand with scalable oversight methods, where the weak supervisor interacts with the strong model to enhance the quality of the weak supervision. In high-stakes settings, we need to have a high degree of trust and reliability in our methods for aligning superhuman models. Strong benchmark performance alone won't provide this. We also need a deep understanding of exactly when and why our methods work. We need to answer questions like, what causes the difference between the strong results on NLP datasets and the poor results with reward models when using naive fine-tuning? What makes a concept easy or hard to bring out? What is a good definition of salience? Can we reliably estimate generalization error at test time without any labels? Can we measure the degree of weak to strong underspecification? Can we reliably extrapolate generalization error across many orders of magnitude using scaling laws? How important are the errors in the weak supervision, exactly? How do different types of weak label biases affect generalization? How robust are our proposed methods to optimization pressure? In our section on understanding, we've only just begun to understand weak to strong generalization. Future work will need to delve much deeper. One advantage of our setup is that it allows us to conduct simple experiments to scientifically study generalization phenomena across a wide range of settings. We would like to express our gratitude to numerous individuals for their valuable technical insights, discussions, and feedback on earlier drafts of this paper. We also appreciate the infrastructure support provided by certain team members. We are particularly thankful to Dan Hendricks, Jacob Steinhardt, and Paul Cristiano for their formative discussions over the years.